Did they get the beer machine fixed? Well, I see beer, so it must be yes. Somebody told me the last one the beer wasn't working correctly, so I just wanted to double check before I walk all the way over there. Well, thanks for being in our afternoon session. We're going to talk about symbolically executing a fuzzy tyrant with our friend Lojikil.
All right. Thank you very much, everyone. I will be talking about symbolic execution, fuzzing, that sort of stuff today. I have a flair for whimsy, so you'll notice that this is mostly using Nabucco, Verdi's Nabucco as a theme. Has no tie-in whatsoever, but you'll see it throughout the talk. My name, though, is Stefan Edwards. I am the assurance practice lead at Trail of Bits. If you're not familiar with Trail of Bits, we are a low-level, cybersecurity research firm. We do lots of blockchain sorts of stuff, fintech, reverse engineering, those sorts of things. You may be familiar with our tools. I myself work in defense, blockchain, IoT, compilers, that sort of stuff. A lot of our vCISO services, procedural services go through me. And I also do our threat modeling things. If you read the Kubernetes threat model, or if you saw the Kubernetes technical assessment for the CNCF, that was myself and my team at Trail of Bits. You also may have heard me on Absolute AppSec or Risky Business, which just came out, I think, yesterday. So just two warnings. I'm extremely hard of hearing. I'm also extremely sick at the moment, so my hearing is completely gone. So if you have questions and I ask you to repeat 37,000 times, it's just from that. And then I'm also from New York. I slept enough, so my accent shouldn't come out. But if I do speak too fast or if my accent's too thick or anything like that, just let me know. So what are we actually talking about today? Today we'll be going over some of the basic tools that we use to understand code, right? And then we'll move a little bit deeper into the stack of things, and I'll explain what I mean by that as we go through. But I wanted to talk about first the two major ways that we attempt to understand code currently, and then try to suss out what sort of coverage we get from those things. And then move into fuzzing, understanding what maybe we think of as fuzzing versus what someone from Trail of Bits or from some of the other speakers, I think Jared DeMott is speaking on symbolic execution and fuzzing later, but what others may mean about fuzzing and that sort of thing. And then move into symbolic execution, what it is and what I'm using it for in my personal time. I'm releasing a framework today. And I apologize, I'm presenting out of MARP. Normally I don't, but for some reason MARP is generating a bad PDF today. But this talk mainly covers three things. I really want you to understand that we can do better than traditional tooling, right? The sorts of things that we run to understand code, we can do much better than that for malware, for pen testers, for whoever you are. And then I want to explain what the hell does this actually look like, right? Very frequently you'll see things that reference formal tooling, formal verification, symbolic execution. It's not really nearly as scary as it might necessarily sound. The framework that I'm releasing today, it's up on GitHub. It was written in about a month. It does some path exploration and things like that. It's very simple. It's very straightforward to follow. But these sorts of things are not used by the vast majority of folks because it's like this hidden area of academic infosec that we don't normally touch upon. And then the last is how to make these things much more accessible, right? There's lots of papers on these sorts of things. Fabrice Godefroy will publish on these sorts of things. We've published on these sorts of things. But they're not really accessible for normal folks. People don't think of these sorts of tools when they're thinking of, how do I understand my code? How do I understand what I'm doing? So I want to try to break down that barrier and make it a little bit more accessible. But if there's three things that you really take away from this talk, is that there's nothing wrong with the way that we do traditional tooling. For code, for pen tests, for those sorts of things, there's absolutely nothing wrong with it. It does have its place. I'll talk later, but as much as I love symbolic execution and think it's super interesting, lots of findings can come out of it, I still find most of my findings either with fuzzing or with my own two fists. Very little of what I find is necessarily from symbolic execution. Symbolic execution, concolic execution, those sorts of things, they help a lot. They help me understand the constraints under which things execute and whatnot. But traditional tooling still shouldn't be thrown out just based on anything that I'm presenting here today or Jared or anyone else presents. And that Formal verification techniques themselves are not actually that scary. They're very accessible once you understand what they're doing, once you understand what they're actually, how to use them. They're not very difficult to get into themselves, even though they might necessarily be a little bit more academic than what you're normally doing. And then lastly, I wanted to just give a really quick, really brief introduction to the sorts of program analysis things that we do. So what is actually program analysis? Right? Programs actually have a space over which they execute, and I'll demo what I'm talking about in a minute. But there's a large space that we intend. So if you think about your program as a graph and all the things your program can do, you probably intended for it to do a very small slice of that entire graph of potential actions. And yet attackers, people like myself, reverse engineers, whomever, will discover the entire set, the entire domain of operations that your program can undertake. So that's what we're attempting to uncover. We're attempting to find the ways in which your program can operate in unintended consequences. And there's multiple techniques for doing this. I'll talk about fuzzing, the various techniques of fuzzing. I'll talk about symbolic and concolic execution. But there's a large world of both academic and practical methods for actually uncovering these sorts of things themselves. But effectively, whenever you hear me say program analysis, you can just think of it as very fancy, potentially automated, and very formalized debugging itself. So has anyone heard of weird machines before? Perfect. One person, two, maybe. So weird machines is this actual area that I'm talking about. These are the sorts of things that your program is normally meant to do. You may have codified it to accept some user input and do something on it. And then there's an entire universe of other things that your program can do from unintended consequences. And these are called weird machines. There's several names for them, but that's the most common name that you hear. And there's many different techniques for actually exploiting, discovering, and actually using weird machines for all sorts of fun things. So I think the most interesting one are the three that I've picked here. Everyone knows ROP gadgets, right? Yes? At least have heard about them. Right? So ROP gadgets are certainly a type of weird machine. But I think the more interesting ones are that the move instruction on x86 is actually Turing complete. So you can use move, no other instructions whatsoever within x86 to completely encode effectively any program that can be encoded in a Turing machine. So that's a neat one. And then Python's Pickle is also another one. Python's Pickle is a serialization format similar to like JSON or something like this, but it's actually implemented as a virtual machine. So most folks use it to store class or maybe some structured data in a dictionary or something like that. But Pickles can actually execute all sorts of functionality external to that. So discovering those sorts of things is a lot of fun. If you ever see things that use pickles or consume pickles from untrusted sources, you basically have remote code execution. And it's fun because I've actually created a REPL that compiles a small subset of Python into pickles and then executes it on the target machine. So when I'm thinking about programs, the techniques that I'm talking about will fit into one of these areas, right? In the top left over here, we have the potential domain of your entire program. And ideally, we have this little box that we expect our program to actually execute. That's what we want our program to execute. But the ways in which we actually discover if our program does that vary to how much they actually map to our ideal. So traditionally, we may have spot checks. We may think of something, check it, and then we'll put a little dot, and hopefully those form together for a little box. We may create tests, but these tests can test anything that we want them to. They don't necessarily have to test anything that's related to the program itself, correct functionality. We have no idea what they actually end up testing. We can fuzz the bejesus out of something, right? We can have this giant Oort cloud of things. We have no idea how this relates to things necessarily. And then we can use these higher level techniques that I'll be talking about today, abstract interpretation and symbolic execution. But those don't necessarily get you to an ideal either. They may map out a domain of what your program is doing, but it doesn't necessarily mean that it maps to your intended domain. I know this is crazy, and there's probably a lot of people who are thinking, what the fuck did I just walk into? But I'll hopefully explain most of this. But more than anything, I want you to walk away with this talk, or from this talk, that you can understand code using automated techniques, discovering constraints, discovering these sorts of weird machines that are in programs, that are in software that you'll be using, and apply them to the domains that we work in. I, at Trail of Bits, obviously run the assurance practice. I do quite a bit of the normal code reviews and those sorts of things, right? We do high assurance work at Trail of Bits, but still, we look at a lot of code. So for us, understanding code is bread and butter to what we do. But there's nothing stopping folks who work in malware analysis, who work in reverse engineering from applying many of these same techniques. And indeed, there are mechanisms for applying what we'll be talking about today to like reverse engineered code. So before I dive into those higher level techniques, and before I dive into the sorts of things that I think are better, that we can be using, let's talk about some of the traditional tools that are out there. So traditionally, we have two basic divisions, right? And this is probably semi-controversial to say this, but there's two basic divisions of what we're talking about. We either have dynamic testing, in which we're actually exercising the system under test, an application, code, whatever it is, and we have static testing. And that's the usual dichotomy that we see. So these are the sorts of things that might scan code, look for misconfigured credentials, look for default credentials, that sort of thing. Or they would go through, you'd see your fortifies, your rats, your splints, those sorts of things, and just look through for dependencies. This is the traditional stack. As much as we want to move beyond this is really the dichotomy that we focus on, even though we can move beyond these sorts of things. So, in a static world, we've all seen linters, we've all seen those sorts of like code check tools, we'll look at some today. Unsafe function checkers, basically things that either look through for strings, grep for things, whatever they are. And then we have the dynamic runners themselves. If you work in MySpace, they may be something that, goes through a web application, goes through blockchain, exercises ERC20 functionality, something like that. Or it may just be malware that you run in a sandbox. But those fall into basically the dynamic domain themselves. And these are the simplest possible tests that you can run. These are the sort of like, you must be this tall to be audited sorts of tests that you have. And whilst they do provide usable findings and usable bugs, they're usually lower quality or lower issue, lower severity sorts of bugs. For several reasons, right? And we'll get into that. But partially because you just don't know much more than the actual location that something has occurred. So, let's take a quick look at this. Some C code, right? Not everyone's going to know C, but just some simple code here, right? This is actually something that I use for interviews when folks come in, right? Now, hopefully several people have spotted a few different bugs here, but there's actually a subtle bug in here as well that not everyone catches. So we have some simple C. So, the simplest possible type of scanner that you can do is something that just checks for strings, right? We've all done this. We've grepped through some code. We've used ACK through some code. We've used rats for things to look for strings within code bases. And indeed, rats does actually find some things in here. There are some problems with this source code that rats actually captures. So we do get two hits. The call to gets is incorrect, and the call to stir copy is problematic. The fgets recommendation itself is fine. There's nothing wrong with what rats suggests for fgets instead of gets. The stir copy one, is everyone familiar with stir, or is anyone familiar with stir copy itself? A few folks. So stir copy one is not so useful. But it's about as simple as we get. We have no setup time. There's no understanding. Literally anyone can run this code and look for things that are problematic here. So we may want to upgrade ourselves. We may want to see, okay, look, rats doesn't give us very much information. We'll run Splint. Splint does some higher level checks. It reports 6 things. Some of them are initialization related. Some of them are type related. Some of them are function related. Perfectly fine. The problem with Splint is that of those, 2 of them are false positives. There's the getS finding, and there's a potential memory leak with our use of foo. However, despite the fact that stir copy is extremely problematic, Splint doesn't actually recommend anything to do with it, right? Because Splint can't determine intention for what we're actually intending to do here. But it's still pretty simple. We do something a little bit better. We get some better findings out of it. But there's lots of false positives, and even these things are completely fooled easily. Has anyone ever seen PMD, run PMD, and gotten clean results from it, and then looked at the source code and noticed that someone put no PMD at the top of source code, which means don't run PMD on this? So I've had developers who, when things were failing in CI/CD pipelines or things like that, instead of fixing it, they just add no PMD so that it stops failing. But that also means it stopped being checked. The other interesting thing is that the stir copy is completely wrong. So stir copy's arguments are actually backwards. This is a Unix historical tradition or convention. And neither one of these tools noted that we were actually using foo, which is the source, for the destination there. So at this level, when we have these sorts of lower level traditional tools, things are very easily confused. There's lots of false positives, but we basically have a lot of things that we can triage for minimal effort. And indeed, these all go back to the way that these tools work. They don't model things necessarily too strongly. For example, RATS is literally doing this. It's literally highlighting boxes in your code and says, hey, this is probably problematic. There's nothing that you can do that's safe about these sorts of things. So at a simple model, right, and we all form mental models. Doesn't matter if you're developing code, doesn't matter if you're analyzing something, you develop these sort of mental models yourself as well. So this is the sorts of model that RATS is actually using. Splint is a little bit more formal. It actually builds up a tree of things to walk. All right. And that's how it does this sort of coloring on objects, right? So it knows that foo, if you remember back to the actual code that we have, it remembers that foo is nullable. That foo itself actually could be null and could be passed into these sorts of problematic functions. So it does some sort of checking. It actually understands the model of the code that it's executing, right? And so it can actually capture more things. Whether or not those are false positives, that's left to behold. But it actually does build up a greater understanding of things and greater understanding of programs themselves. And the model of things impacts what we actually can test. It impacts what we understand about our code itself, right? So we have two strings here. We stir copy one into the other, and then we attempt to printf, right? And Splint, based on its model, realizes that the stir copy, the initializations, and the use of all of this functionality is completely acceptable. But RATS still warns you, and now you have to go back and triage what's actually happening in the code itself to actually understand what is being impacted here, which at the end of the day is nothing. So you get these findings very quickly, you get these issues very quickly, and then you end up having to triage them much more because of the sorts of things that you have here. So, yes. So, what we're trying to do is actually form models of our code. This is from a ideation that I was having as I was talking through some of these sorts of things. And on the static side, we have the simple string searches, regexes, linters, taint, and then symbolic execution. And dynamic side, we go down in power. But as we're attempting to understand code, we're attempting to go down this list on either side until you get to something like abstract interpretation, which straddles both sides. We're trying to go down and gain understanding of our code and gain understanding of the exploits, issues, and surface area of our code itself using these techniques. Does it make sense to everyone? Probably yes, no? Yeah? Cool. So, let's talk about fuzzing. I think people have a notion of fuzzing. They think of it as just random testing. It's not necessarily what we always mean. But fuzzing itself is an extremely useful technique. Probably everyone has seen it or used it in some fashion. But I want to talk about what we mean by fuzzing versus what is often used as fuzzing itself. So traditionally, people think of fuzzing as just throwing random garbage at an application, right? You can think of, reading out of dev urand or something of this nature to throw at an application itself. That's not what I mean when I say fuzzing. I'm talking about mutation testing and I'm talking about property testing. So we can do something like we're given a valid input from an application. We're given something from an application. And we bit flip that to see and watch what an application does, right? That's the sort of mutation testing that we had. So we start from a valid input, we mutate it as many times as possible, see what the application does, see if it crashes, right? And this also can be highly structured, right? So I've had applications that required some form of JSON in. We don't want to fuzz the JSON parser. That's probably not useful to the end user, right? We want to actually fuzz the application itself. So there are techniques and there are ways of doing these sorts of things via property testing and via other related tools. And these are in most folks' tool sets, right? People use the FuzzDB, they use SecList, they use Intruder if they're using burp, right? They have these sorts of things. It's completely normal, right? But we're not actually mutating program state with many of these. Right? Think about SecList, not to pick on Daniel, but to think about SecList, right? If you're looking for XSS or you're looking for something in an application, if you just run SecList, it's a literal huge list of XSS payloads. Super useful. You may discover something there, but it's not actually mutating program state. There may be things that the program is doing that are contextually interesting for what the program is that will never be found by just throwing a random list of words at it. So, we're trying to uncover the light yellow portion of our applications by throwing random data at it. And mutation is one of the most useful ways that we can do those sorts of things. So this is the easiest example here. We're looking for something that's a string, right? We may just throw random bytes at it. They may be valid ASCII, they may not be, they may be UTF-8. We have no idea. We don't care. We're just throwing random data at our application. If we're doing mutation testing, we actually take valid data and then output n variants of it. Has anyone used Redomsa before for fuzzing? No? So Redomsa is a naive fuzzer. It does mutation testing. It has many different techniques and algorithms that you can use for these sorts of things. And I've found a large number of vulnerabilities just by running Redomsa at things. We can also have grammar-based fuzzing. So basically, we describe the data. We describe how things work. So for example, I've done grammar-based fuzzing by describing the instructions of a virtual machine, describing the opcodes and the operands, and then having something randomly walk through and generate grammars of these sorts of things. And then we can have property testing. So property testing is like unit testing on steroids. Probably the easiest way to describe it. We describe some set of invariants, we describe some set of properties within our code base, and then we run random generation on these sorts of things and see what we can actually cause to break. And perhaps not, with things like AFL, we can actually implement or instrument our program to see what the actual state is itself. So the goal is to get greater depth, right? Beyond what humans can see. And we do see these sorts of results. I myself have had 57 bugs just from Redomsa in the last 2 years. Doing nothing else. Not being smart about it, not being, not modeling anything, not actually attempting to go into any depth with these sorts of things. I've had 57 or so bugs, say 50, right? And AFL actually has to maintain a repository of all of the bugs that it's found. So we're clearly finding some random, we're clearly finding some issues with random testing, right? Bless you. But can we actually tell what we're covering here? Right? If you throw random data at an application, do you know what you're getting out of it? Do you have any idea if that state was intended, if it wasn't? And like, what are we actually getting out? We can watch for crashes, but what if the application doesn't crash? Right? What if it just gets into some weird state and continues to hang? We've seen these sorts of things before. Kubernetes itself, fuzzing it. There are ways to make Kubernetes like kubelet hang, or ways to cause things like blockchains to hang that don't produce any actual valid results. But that doesn't mean that we can watch for a crash. They never panic, right? So we have to have some understanding of what we're actually looking for in order to get this sort of coverage. And we can, right? We can use things like AFL. AFL, American Fuzzy Lop, It is a tool for actually instrumenting binaries or code. It hooks in, watches which paths things work down, fuzzes those. And we can also spend time specifying property tests. So if you've written unit tests before, imagine writing these sorts of tests and saying, hey, no matter what happens, this function should never fail, right? Based on this property. You can do this and have a tool actually randomly generate that. But the amount of time that you actually spend doing that is very high compared to what we maybe would want to do. We want that sort of like quick fix that we have with the sort of rats and splint and things like that. And we can use newer techniques too. Gray box fuzzing is a new technique that's out. Super interesting if you're fascinated by these sorts of things. Gray box fuzzing is interesting. But no matter what we're trying to do, the whole purpose of this is to discover that light yellow area in our weird machines picture. We're trying to find and exercise new functionality within an application itself. So we need to uncover these paths, right? Because programs themselves are just fancy graphs. Has anyone seen graphs of programs before, like a control flow graph or a data flow graph? Sure. If you've done any reverse engineering, if you've done any code analysis with compilers, those sorts of things, programs themselves are just graphs. There's some constraint, there's some basically Boolean check or whatever there that specifies some condition under which we execute this piece of code, this portion of code. And then we also are constrained by input, right? Doesn't matter if it's user input or if it's system input, we're constrained by these sorts of things. But really the question that we're trying to ask is, can we discover and graph all paths within an application itself? So let's talk about symbolic execution. So program space itself is usually quite wide, right? There's lots of things that go on in an application. There's lots of things that happen within an application that we want to discover them without having to do much ourselves. We want the cheapest, fastest way to discover these sorts of things. And symbolic execution can certainly work there. And one of the things that I'll be introducing is what I've been working on for the last, month. It's not a month's worth of actual time. It's bits and pieces here and there as I need things. But programs themselves are just graphs. They're textual graphs that we write things together and string them together, right? Nodes represent some sort of action within the system, and then we have edges that represent constraints. So think about this code. This is some simplified code that I've seen many times. I'm sure everyone has seen things like this. So we have an if and we have an else. We undertake two different actions, depending on if j is actually less than k. So there's actually no difference between those two programs, right? The textual representation before can be just as easily represented as a graph here, right? We don't know what j and k are, so we set them to some lambda. We don't know. There's some value to say symbolically we know that these are two different values, or we suspect they're two different values. And then we have this graph. On one side we know that j is less than k, and on some other side we know that j is greater than or equal to k. That's the dichotomy of this program itself. So what we're actually attempting to do is provide these graphs or find these graphs, generate the constraints, and then solve them. Has anyone seen constraint solving before? Yes? So constraint solving is basically a system that takes a SMT formula and then attempts to apply a bunch of binary techniques to generate these sorts of things. There's bit bashing and a lot in here. My focus is mostly on combining fuzzing with symbolic execution, but nonetheless, there's various means by which you can actually generate these graphs, generate these constraints, and then solve them. And it's extremely useful. CLI is helps if I don't lock myself out. CLI is a common one that works atop LLVM. We at Trail of Bits have a symbolic executor named Manticore. Consensus Diligence has one named Mithril, MythX now. And these two, Manticore and Mithril, are both used in the blockchain space quite heavily. Right? So if you have Ethereum code, you can symbolically execute them and understand your programs much more deeply just with using Manticore or Mithril. So the problem with many of these tools, though, is that they generally tend to work on binary code itself. And if we're doing malware analysis, my side interest is in malware analysis, especially with languages, right? I'm kind of curious how we get safe execution of Office macros, of JavaScript, of JScript, those sorts of things. And we want to uncover second stage things in a safe environment. And I'm kind of tired of setting up a VM to do these sorts of things when we have better techniques and better tools to handle these sorts of things. And the other thing too is that very frequently they require full code bases. I don't want to walk through your entire code base. I want to see something that looks extremely interesting in the middle of your code. I want to pull that out, execute it, and find the constraints itself. So I've been working on this unnamed Symbex project number 9. There's been several other ones that I've written either for clients or written for myself. But it's live right now. You can go look at it. It's basically a high-level language symbolic execution and constraint environment. I'm not focusing on the sorts of Z3 and those sorts of constraint algorithms themselves, but it's certainly a possible area. And there's a whole list of references up there as well if you're interested in these sorts of things. But what I'm actually looking for is a few different things. I want it to be able to work on partial code. Like I mentioned, I don't really care to execute your entire program. If you're familiar with symbolic execution, search spaces will explode if I have to execute your entire program. And I also want it to be safe by default, especially because I want to run malware in this thing. So I want something that I can run arbitrary malware, not on a sandbox, and not have to worry about what's happening in the background. So that's where I'm working here. It's roughly a month old currently. But the way it works is it translates languages like JavaScript into an ugly scheme dialect. Does everyone remember scheme from school? Like if you went in colleges, it's the last time most people have seen it. I actually was a professional scheme programmer for a while. But it's basically a scheme dialect and a Python library for interacting with it. And it handles two different edge cases. There's concolic execution, concrete execution. This is what we normally think of as execution when we execute code. We concretely go through, we get a set of values, we execute those values, return them to the user, display them, run them, however it is. And then we have symbolic execution. Now, symbolic execution we'll go through in a second, but it's basically working on unknown data itself. We don't know what it is. We don't know what the constraints are. We want the application to tell us that. So we want to map program space itself. So in this code itself, I generate two concrete integers themselves here, f and g, and I just add them. Now, that's not in and of itself interesting. Where this becomes interesting is that we have the trace that's here. So in this system, every single value is tagged. So you can actually look through and find even where constants are used. So for example, if the number 10 exists multiple times within this application, you'll actually see the unique location that 10 is actually instantiated each and every time within an execution. And then we have the trace. So we have the execution path by which we actually got to this value. So it's not useful to know that h is equal to 21. We don't care about that. We want to know where and how we got to 21. And these sorts of value constraints and these sorts of value traces allow us to do that. But more interestingly is when we can work on unknown or symbolic data here. So here's a relatively simple, almost the same program. But now G is symbolic. It means we don't know what value G actually represents. Right? So here, when we add two values, we just say we have 10 plus something else. Now we know for the lifetime of the program that h is always 10 plus whatever the value of g is. We have no idea what g is. We may solve it, we may not solve it. We may fuzz it, we may generate it, we may constrain it ourselves. We may say, hey, later on in the rest of this program, g is actually equal to 20. But from now on, the program actually can trace and follow that h itself is always 10 greater than whatever the value of g is. And then we have these unique tags themselves, no matter what. So wherever we see that UUID, and I'm using UUIDs because that's the easiest way of getting fresh things. But no matter what we do, we can see where those values came from themselves. So who actually cares about this, right? Like, why do we care, right? Why do I care about these sorts of things? Well, it becomes interesting when you actually start to look at constraints themselves. So this is what the scheme dialect itself looks like. If you haven't seen scheme, I apologize, or Lisp itself. But basically, we have some variable foo, and we have no information about it. It's purely symbolic to us. And under certain conditions, we return 12, and under certain conditions, we return 13. But we know nothing else about foo. We only know these sorts of path constraints. So we can start to ask these questions. I know this is a little difficult to see, but we can actually start to ask questions here. So the first one, we have two virtual machines here. We have test VM1 and test VM0. So test VM0, it has some value for foo itself. It has this information. So when we execute foo, when we execute this if, it actually knows and can provide a value. It says, oh, hey, under these constraints, we actually get a path execution that returns the value of 12, and it does it under this condition. So USP varref AST says when foo is true. So foo itself under this path execution is true. Now, we may have another path execution. So in VM1, we have no information about what foo is. So VM1 actually says, hey, there's two different paths that we have to walk. There's one path that's false, right? Foo is false itself. It definitely has to be a Boolean, and we have no idea what that returns. But under that path, if the application was false, we actually get a 12. And then if it's true, we actually get 13. We get these two different paths, and they walk the same constraints. So the program is actually telling us, under these conditions, we either have a concrete execution, we execute some path, return it, or we have a fork. The program doesn't know which direction we go, and you have to figure that out. You have to start to walk. This can be extremely useful if you have a giant nested if you have something that relies on environmental data. So for example, certain malware will actually check how many files you've opened recently on the system. And if you're in a virtual machine, you've probably opened not enough, right? Because you're not actually interacting with this system as a normal system. You're not actually opening things. You're not running things. You're not running programs here. Well, symbolic execution allows us to say, hey, under this condition, under this constraint, the program will do X and split and fork there. So we can then start to trace down and say, okay, that's interesting. Let's continue execution from there. So we want to find the constraints under which things execute, and symbolic execution allows us to do this. It has many problems, but it's extremely easy currently to at least get path constraints here. And one of the things that I am very interested in is the new techniques that actually combine symbolic execution and fuzzing. The sorts of gray box fuzzing, the sorts of like learning inputs for applications. So that's my next step, is to actually go through and say, hey, if we see something that looks reasonably like it traces through to a sink that is XSS, let's try XSSing this. Let's try something that's contextually relevant based on the constraints that we have, and let's actually attempt to execute that there. And then also, we have both concrete and symbolic execution. So we can go through with unknown data, we can go through with valid data. So if you have valid data, you can execute this as well. And I support both micro execution and standard execution throughout. Now, has anyone heard of micro execution before? No? New technique? So micro execution is actually an extremely fascinating technique. You literally run one form or one instruction. A form is a syntactic form, like an if block or a function call or something of that nature. And you provide it with a stack, an env, all sorts of things that you need to set up. Maybe some user input, maybe not. But you literally run this one instruction in the stack, in the environment, in whatever you have set up. Now, why is this interesting? Because you can continuously manipulate the other factors to this instruction and see what it does to the environmental variables. So for example, if you wanted to discover that move was Turing complete, you could provide a stack, you could provide certain, certain register values and see what move actually does based on the execution path that you see for each single time that you call move. So you change nothing else about the program other than the stack, and you micro execute it. Trail of bits, we have a certain section of the company called lifting bits. It deals with binary representations to higher level representations. But we do have a micro executor called MicroX. And then Patrice Godefroid has actually worked on this quite a bit. Microsoft has quite a bit of work into micro execution. But it's a super fascinating technique. And one of the things that I wanted to explore was, how does this actually interact with high level languages? And USP number 9 is actually part of that. But there's a lot to do. If any of this is actually interesting to you, I'd love to talk afterwards. But there's quite a few things that I want to do here. I want to flesh out the JavaScript parser that I have. Currently, it's quite manual. There's quite a bit that's going on in there. I want to do a normal form and single static assignment. ANF and SSA are super useful, and lambda lifting. So lambda lifting basically takes anonymous functions from an in situ representation and moves them to a higher level, and then passes in anything that's captured from that lambda. And I want to add a ton more tests and strategies. So if you're interested in fuzzing and you want to understand code more, I'd love to see PRs and polls to help with some of the generation strategy. But my use case is I want to understand gnarly code that I get from either clients, from malware, from those sorts of things. And I want to exercise them as much as possible. See under which constraints these programs work, see how things are going, and then actually execute them without having to know the entire code base, without having to understand much here. And that's what I'm using this for. So I'm a bit early, but that's it. Thank you very much, everyone, for coming. Does anyone have questions? Since I can now I can be tortured by questions here. No? Everyone awake? Yeah, sure.
When you say execute gnarly code, do you mean, are you applying this to just sections of code or an entire application at a time? Or does it
Sure. So the question is, if you want to execute gnarly code, are you just doing sections, the entire application, that sort of thing? My use case is very frequently when we have, say, Go code or JavaScript, TypeScript, that sort of thing, I want to know what this section is doing. I may be able to understand how to get there, but I want to know what this is doing. And I don't want to include the rest of the execution path. I don't want to walk through. So yes, I want to just rip this out, see what this thing does, and then walk back to those constraints myself. And then you can obviously do control flow graphs to get there. You can do other walks to get back to it. But mine is to really pull out in situ sections of high level code and do those sorts of things. So for example, in Go, in JavaScript, you manipulate the stack quite frequently, right? You may have defers in Go, you may have continuations, those sorts of things that manipulate the stack. I want to mechanize those to CPS or ANF and then actually walk through those constraints there themselves, just for that one function, instead of the entire search space of an application that can break. Does that answer your question? Yes. Quite fully. Anyone have any other questions? Well, perfect. Thank you very much, everyone, for coming. It was a pleasure.